Welcome to Prof.Ahilaa Max, Plus 2 Mathematics, Tamil Nadu State Board Syllabus, Chapter 1, Application of Matrices and Determinants, Video 1.14, 1.3 Elementary Transformation of a Matrix, 1.3.1 Elementary Row and Column Operations, 1.3.2 Row-Echelon Form, Definitions 1.4 and 1.5. 1.3 Elementary Transformations of a Matrix. A matrix can be transformed to another matrix by certain operations called elementary row operations and elementary column operations. Elementary row and column operations. Elementary row and column operations on a matrix are as follows. First operation is the interchanging of any two rows or columns of the matrix. Second one, replacing a row or column of the matrix by a non-zero scalar multiple of the row or column by a non-zero scalar. Third point, replacing a row or column of the matrix by a sum of the row or column with a non-zero scalar multiple of another row or column of the matrix. Elementary row operations and elementary column operations on a matrix are known as elementary transformations. We use the following notations for elementary row transformations. First operation, interchanging of ith and jth rows is denoted by Ri interchange with Rj. Second one, the multiplication of each element of ith row by a non-zero constant lambda is denoted by Ri goes to lambda Ri. Third operation, addition to ith row, a non-zero constant lambda multiple of jth row is denoted by Ri goes to Ri plus lambda Rj. Similar notations are used for elementary column transformations too. Instead of R, we put C. So remember, for interchanging any two rows, we use Ri interchange with Rj. For multiplication of any row with respect to some non-zero scalar lambda is given by Ri goes to lambda Ri. And we can add any row or column with a particular row or column by multiplying by a non-zero scalar. That operation is given by Ri goes to Ri plus lambda Rj. Definition 1.4 Equivalent matrices. Two matrices A and B of same order are said to be equivalent to one another if one can be obtained from the other by the applications of elementary transformations. So remember, all the matrices which are equivalent should be of same order. Symbolically, we denote as A equivalent to B. We don't say A equal to B. Okay. So equivalent to B to mean that matrix A is equivalent to the matrix B. Now consider the matrix A, a 3 by 3 matrix, 1 minus 2, 2, minus 1, 1, 3, 1 minus 1, minus 4. Suppose I want to make this element, that is A21 element, okay. I want to make this A21 element in the R2, row 2 to be 0. So for that, I will compare with the other elements in the same column and the corresponding row. I can use any element to make use of this particular element to be 0. So here I am considering A11 which is 1 and A21 is minus 1. When I consider 1 and minus 1, my aim is to make this minus 1 as 0. So I can add these two elements. Okay, we cannot add a particular elements. Instead, we should either make the operations to the whole row or column. Okay, so I make R2 goes to R2 plus R1. But with respect to these two elements only, I decide the operation. Okay, but the operation is given to the whole row. R2 goes to R2 plus R1. I have to consider all the elements in the rows. Okay, so now consider R2. the elements in R2 are minus 1, 1, 3. And that of R1 are 1, minus 2, 2. Now I need to add. I am adding all these elements. So minus 1 plus 1 is 0. 1 minus 2 is minus 1. 3 plus 2 is 5. Thus I am getting that particular element 0. Now replace these values in the matrix. Here I put equivalent symbol. Okay, because the matrices are not equal. The first row I don't change, so I keep the first row as it is. Similarly, the third row also I don't make any changes, so I keep the third row as it is. But only the second row gets the value by adding R2 and R1. That is 0, minus 1, 5. Okay. So if I consider this matrix as B, I can say A is equivalent to B and but A not equal to B. Okay. So thus A is equivalent to B, because if all the elements for equality, the matrices should be in same order, as well as each and every corresponding elements should be equal, the same. Then only we can say two matrices are equal. Equivalent means by making elementary transformations, we are reducing some matrix to another matrix, means we can say those matrices are equivalent. Got it? Let us see the note. An elementary transformation transforms a given matrix into another matrix which need not be equal to the given matrix. So row-echelon form. Using the row elementary operations, we can transform a given non-zero matrix to a simplified form called a row-echelon form. So row elementary operations, making use of row elementary operations, we try to get row-echelon form. In a row-echelon form, we may have rows of all whose entries are 0. Such rows are called zero rows. If all the elements in a particular row is 0, then we say it is a zero row. A non-zero row is one in which at least one of the entries is not 0. Suppose in a row, at least one element is non-zero, then we don't say it is a zero row. It is said to be non-zero row. See this example. A 3 by 3 matrix, 6, 0, minus 1, 0, 0, 1, 0, 0, 0. Okay. So here which is the 0 row? The third row contains all 0 elements. Okay. So it is called the 0 row. R3 is said to be 0 row. But consider R2. What about it? That is A, 2, 3 is 1. It is not 0. Therefore, we say R2 is non-zero row. Similarly, we can speak for columns also. So, when we consider the second column, it is 0 column. Suppose we consider the first column, we are having 6 non-zero element in it. So, we say it is C1 is non-zero. Definition 1.5. A non-zero matrix is said to be in a row-echelon form if first point all 0 rows of E occur below every non-zero row of E. Second point, the first non-zero element in any row I of E occurs in the jth column of E, then all other entries in the jth column of E below the first non-zero element of row I are zeros. Third point, the first non-zero entry in the ith row of E lies to the left of the first non-zero entry in I plus jth row of A. Note: a non-zero matrix is in a row-echelon form if all 0 rows occur as bottom rows of the matrix, and if the first non-zero element in any lower row occurs to the right of the first non-zero entry in the higher row. Simply saying, the bottom rows should be 0 rows. Okay. So, see the 4 examples here. When we see the first matrix, we are having the third row 0 and the leftmost elements are 0 as per the second and third conditions. Okay. So, it is in row-echelon form. Similarly, the second matrix also in the row-echelon form. But the third and fourth are not in that form because we are having zeros in the right side. It should be in the left side, and from the bottom it should be bottom rows, the 0 rows should occur. So the third and 4 are not in the row-echelon form. But we can convert to row-echelon form by using elementary transformations. Thus 1 and 2 are in row-echelon form and 3 and 4 are not in row-echelon form. Understood? Simply remember, row-echelon form is nothing but upper triangular matrix. Okay, the lower rows should be in the 0 form. It is not the must that all the rows in the bottom should be 0. It is not the must condition, but it should represent a upper triangular matrix. Method to reduce a matrix M by N matrix to a row-echelon form. Step 1. Inspect the first row. If the first row is 0 row, then the row is interchanged with a non-zero row below the first row. So we should keep the first row as non-zero. Suppose the first row is 0, then we can interchange with the last row. Okay. So because our aim is to make the bottom rows to be 0. If then we need to check for the first element A11. It should not be 0. Okay. Suppose it is 0, we can inspect with the corresponding row elements and the column elements. If we can interchange accordingly, such that the first element in the matrix should be non-zero. So making such a thing is called pivoting the element. Okay, because we use that particular element A11 as the pivot element to make the elementary operations. So our aim is to make first to check the non-zero row of the first row. Suppose first row is 0 row, interchange with any other row which is non-zero to the bottom. And then inspect A11, the first element. It should not be 0. Suppose it is 0, you interchange with any corresponding row or column elements. Then making that as pivot element, we can consider that particular first row as the pivot row. Okay. Step 2. Use the first row and elementary row operations to transform all elements under the pivot to become zeros. Step 3. Consider the next row as first row and perform steps 1 and 2 with the rows below this row only. Repeat the step until all rows are exhausted. So simply saying, we have to remember, we try to make the upper triangular matrix. That is, from the bottom onwards, we try to keep all the elements as 0. When we do such operations for a particular row or column, considering one particular element to be 0, automatically the matrix is converted to the equivalent row-echelon form matrix. Understood? Let us see by some examples and problems in the next video. Video 1.15 contents are example 1.13, 1.14 and 1.15. 1.3.3 Rank of a matrix. Definition 1.6. Stay tuned. Success is ours. Thank you, my dear children.